Hi, I'd like to talk about a very common and very important group of fossils called the cephalopods. Now, cephalopods are mollusks, so they're related to snails, to bivalves, and they're a group that can include modern day octopus, squid, cuttlefish, and crucially for what we're looking at today, nautilus. In the past, there were very diverse groups of shelled cephalopods, what we call the goniatites, the ceratites, ammonites, and belemnites. We need to look at how we can distinguish between these different extinct groups. The nautiloids, ironically the only group to still exist of the shelled cephalopods, were the first ones to appear in the Upper Cambrian. They had long straight shells, but this would limit the size that these animals could grow to. So to evolve a bigger body shell, or a bigger body shape should I say, the shell needed to evolve a coil. Nautilus is a living shelled cephalopod. It's the only one we have still surviving to this day, but as a result gives us an excellent chance to apply uniformitarianism to understand the extinct groups of shelled cephalopods. You can see the picture on the right shows the outside of a living animal. The one on the left is a cross-section through a shell of a fairly obviously dead animal. As the animal grew, as it needed more space for its body, it secreted a bigger shell coiled round on the older bits of its own shell. At different stages of its growth, it would secrete a wall of calcium carbonate behind the body. What that created was a very strong chambered shell. So there are different chambers within this. You can see that there's these little sort of holes with little extensions on in each of these walls. This is where a fleshy tube called a siphuncle would have connected these different chambers. As well as giving strength and support for the body, we think as well these animals can control their buoyancy by putting fluid into or taking fluid out of these chambers. Where these walls are joined to the inside of the main shell, it creates a very distinctive structure called a septa. We'll come back to that. This is a close-up of this siphuncle, okay, showing the chambers. We can also see on the diagram on the right there, we've got the body chamber, the last, most recent part of the shell where the animal actually lived. Often those don't survive very well into fossilization, but the septa, those walls, do give a very strong shell that does preserve very well. Now, we use cephalopods as zone fossils, except we can't use Nautilus. It hasn't changed really for 400 million years. What it does do though is show us how these animals must have lived. We can see the octopus-like animal there in its body chamber with these this chambered shell behind it. They move around, they swim around in the sea by sucking in water and squirting it out, sort of a jet-propelled animal. The group evolved and changed over time. You can see the middle part of this graph shows us the Nautiloids, very abundant back in the Paleozoic, less so as time has gone on, but still existing. The group we're most interested in, though, is the one on the right, the Ammonoids. Now, the Ammonoids, again, you can see, have changed in their diversity. They evolved rapidly after the end Permian mass extinction, and again after the end Triassic mass extinction. But as you can see from the diagram, the end of the Cretaceous was the end for the shelled ammonoids. We recognise 3 distinct types, and you need to be able to do this. They're the goniatites, which you can see the bottom left, the ceratites in the middle, and the ammonites on the right. You can see that the shape of the fossils is very similar. They all have this coiled shell. The key thing that separates them is the shape of the suture lines, where this internal wall meets the inside of the main shell. If we look at this beautifully preserved example, what you're looking at here is a cast of the inside of the shell, with the outer part of the shell probably having been removed by preparation there and polished off, so we can see the shape of the shell. If we zoom in to part of this, we can see where each of these internal walls would have met the inside of the shell, creating a very distinctive, and in this case, quite complex pattern. Now, that complex pattern tells us as geologists that this animal must be an ammonite. We can see from this diagram that the ammonitic suture, the most recent of them, is this very frilly, very complex pattern. The earlier version, the ceratitic suture from the Triassic, is simpler. We start to see some of the increased amount of complexity, I suppose, starting to appear, but there's still quite a rounded shape. The goniatitic suture, more typical perhaps of the Carboniferous period, is really quite simple. And the earliest one, the Nautiloid that evolved in the Devonian, is simpler still. So as we go from oldest, in this case at the top, down to the most recent, down at the bottom of this diagram, we can see an increase in complexity of the suture line. It's that allows us to use these fossils for dating rocks. Now, they're a fascinating group. Some of them, they're incredibly diverse, incredibly common. If you go to Jurassic rocks, perhaps around the south coast of England or of Wales, you can commonly find ammonite fossils. If you go to the Carboniferous rocks in the north of England, you'll commonly find goniatite fossils. Some of them, though, most of them are quite small. There were a few, though, that were extremely large, maybe up to 2 meters in diameter. And a fossil there just to show you that this is the case. These fossils are very, very useful. They give us a really good way of dating quite a large chunk of geological time, starting in the Carboniferous and really going right the way to the end of the Cretaceous. In particular, the Mesozoic era is largely defined by its ammonites. Make sure you complete your notes and come to class with your interesting question. I'll see you then.